is I would like to do any problems that you have on that you need help with on progress check B. So put any ones that you didn't understand in the chat and I will go through any of them for you, or all of them if you need them.
Wait, Alquist, are you recording this one again and putting it on the YouTube channel?
Yep.
Okay, thank you.
Mm-hmm. So I am recording this, like I always do. I did a bunch last hour and didn't record it, but that's because I just did it with Nick Kent last hour. So as long as you have questions, I'll do them. Okay, so I think I have 2, 3, 4, 8, 9, 12. 2, 3, 4, 8, 9, 11, 12. Okay. So we'll get through as many of those as we can. So let's look at 2. I hope my iPad has enough power to hold off. Okay, 1 second. Let me pull up a couple of things on here and get it mirroring. Okay. Okay, so can you guys see the screen? Perfect. Okay, I'm going to open the chat up, but it's really hard to monitor both. So if I do something that you don't understand, it would be super if you just unmute yourself. Okay. Okay. So on this one, a couple things we have to remember. So the first thing it says is F has many critical points, 2 of which are x equals 0 and x equals 6.949. So what that means is if F has critical points at x equals 0 and 6.949, all that means is F prime of 0 and F prime of 6.949 equals 0 or is undefined. That's all that means. It doesn't really give us any other information on there, but we know that that's true. So the next step says, oh, here's the second derivative. Okay, so here's the second derivative. Which of the following statements, and you start to look at them, he says, oh, F is a local minimum at 0 and 6.949 and maximum, and then a local minimum. And so you think about that and you go, well, wait a minute, don't I really need to know something about F? But I'm given F prime. Well, so remember that when, you're given F double prime. Remember, F double prime being positive, F is concave up. So that is a graph that would look like this. When the second derivative is negative, F is concave down. So the graph would look like this. So we know that we have these critical values. If we can kind of merge this information, which we know to be true, with this information, which we can find out, then we can kind of get an idea of, well, what does the graph of f look like? So what it would be really nice is to figure out what is the second derivative of 0 and what is the second derivative of 6.949, because if we know whether the second derivative is positive or the second derivative is negative, we can figure out what the graph of f looks like. So here's what we're going to do is, since this is a calculator based one, I'm just going to graph this, because I'm not going to try to do this on my own. Either way, I'm going to have to plug in values. So I'm going to just graph it. Okay. So I'm going to go here and I'm going to say, okay, well, if I go to the graph and I go to y equals, and I actually had already done this last hour, so I put it in there. It's right there. I need to make sure my calculator is in radians, not degrees. So you need to check and make sure your calculator is in radians. I know that this one is, because I worked on it last hour, but you need to make sure it says radians. And then I'm going to graph this. And when I graph this, it looks like that. And I know that this window actually goes like -10 is back here and 10 is up here. And then -10 is down here and 10 is up here. Okay. So when I take this and I kind of go, okay, well, notice that f of z, this is the second derivative, right? This is the second derivative graph, this blue one. And notice the second derivative is negative right at 0. Does that make sense? This is the second derivative graph. We know that this is negative, which means f is concave down. Okay. And if we go and we look at 6.949, this goes up by 1. So 1, 2, 3, 4, 5, 6. 6.9, it's like right in here. It's also negative. So we know that this is negative. So f is concave down. So what we have on this is we have all this information. We know that these are critical points. We know that if the second derivative is negative, which it is what we have this situation, which means we know that both 0 and 6.949 are graphs that look like this, that are relative maximums right there, or local maximums. And remember, relative and local is the same thing. So the answer is D on this. So that's where we can use the second derivative and the information it gets, whether it's positive or negative, to kind of tell us what the graph of f has to look like. Any questions on that? Okay, let's go to 3. So now we're asked to figure out an absolute maximum on this closed interval. So anytime you're trying to find an absolute maximum or an absolute minimum, let me get this where I can see the whole thing better. And I can blow it up a little bit more. So for an absolute minimum, on this, we got f is equal to 2x cubed plus 3x squared plus 1. We got the interval -3 to 1. So we got to figure out the critical numbers first. That's the first step to figuring out an absolute minimum or maximum. So this is 6x squared plus 6x. So we got to figure out when 6x squared plus 6x is equal to 0. If we factor out a 6x, we'll have x plus 1 here. It's equal to 0. So we know we have critical numbers at x equals 0 and x equals -1. Is everybody with me there? Okay. So actually, I'm not going to ask you if you're with me anymore. If you're not with me, you got to just stop me because it takes too long. Okay. So if you're like, I'm not with you, then just stop me. So the next thing I'm going to do is I'm going to make a table. And I'm going to make a table with these two values, this value, and this value. And then I'm going to use those along with f of x. So I'm going to use all the orange information to figure out what's the absolute highest y value and in this case, what's the absolute highest y value, because it's asking me for an absolute maximum. So I'm going to make a table, and my table is going to have -3. And I usually like to put them in order, in ascending order. So -1, 0, and 1. And here's x, and this is f of x. Okay, so I'm figuring out what f of x is on this. So I got 2 times -3 cubed plus 3 times -3 squared plus 1. And then this is going to be 2 times -1 cubed plus 3 times -1 squared plus 1. And this is 2 times 0 cubed plus 3 times 0 squared plus 1. And then this is finally 2 times 1 cubed plus 3 times 1 squared plus 1. So we can do all of these and just calculate them. And I'm just going to start out with the easier ones. This one clearly is 1. That's the easiest one. I can kind of go with that one. This one, the one at the bottom here, is 2 plus 3 plus 1, which is 6. This one up here is going to be -2 plus 3 plus 1. -2 plus 3 plus 1 is -2 or +2, right? +2. And then the top one is equal to 2 times -27 plus 27 plus 1. Okay, does that make sense? Clearly this is less than 0, right? I mean, I don't have to figure out what it is because it asked me for my absolute maximum. And that first one is less than 0 because of the 2 times -27. So my absolute maximum is right there. Now the question is, what's the answer? Is it 1 or 6? The answer is, it is 6. Okay, because it asks what's the absolute maximum. It occurs at x equals 1, but the value is 6. So you got to figure out what they're asking you. Most of the time, AP, when they ask you for an absolute maximum or minimum, they're asking for the y value. When they ask you for a relative maximum or minimum, then usually they're asking you for the x value in that case. So you got to kind of make sure you know what the question is asking for. Okay. So let me go on to 4. So 4 is pretty similar, actually. Okay, 4 is a pretty similar question. Just uses sine and cosine, but it's the same kind of idea. We're going to actually do the same basic steps where the only thing is finding a critical number on this. If you're not, if trigonometry gives you, makes you break out in hives, this could be troublesome for you. So we still have to find the derivative. And so you get cosine x minus sine x. We need to figure out when that is equal to 0. So we need to figure out when the cosine x is equal to the sine of x. Now, you maybe know where this is. Maybe you have the trig wheel memorized. Maybe you know exactly where this is. My bias is to do it a couple different ways. The first thing I want to do is I want to know which quadrants does this happen in. The easiest way I can figure out where sine and cosine are equal is where do they intersect. So my bias is to kind of say, okay, I know the sine function looks like this out to 2 pi. I know that the cosine function looks like this out to 2 pi. So I know I'm dealing with where they intersect here and where they intersect here. Now, cosine and sine, when they're equal, that's when the reference angle is 45 degrees or pi over 4. Now, the other time that that happens is this is pi. That happens right here at 5 pi over 4 also. Those are the two critical values. One's in the first quadrant when sine and cosine are both positive, and it's when the opposite and adjacent sides are the same, and that's when you get a 45-degree angle. And the other time that that's going to happen is when both sine and cosine are negative, and that's in the third quadrant. If you're like, oh my God, I can't remember how to do that stuff, you maybe need to go back and look at your notes way back, like the first or second day that we were even in class together. We did a trig review, and that's what we did. Okay, so that's the two values. So now what I have is I have to make this table again. I have 0, pi over 4, 5 pi over 4, and 2 pi. And sometimes it helps people if you write x here and you write what you're evaluating here, which is sine x plus cosine x. Now, if it's an FRQ, you're already generating points by finding the derivative, finding the critical numbers, and now making this table is usually another point. And so what I'm looking for is well, when's the sine of 0 plus the cosine 0, what's that equal to? Well, if you know what that is, that's equal to 1, because the sine of 0 is 0, the cosine of 0 is 1. So then you go, okay, well, what's the sine of pi over 4 plus the cosine of pi over 4? Well, so if you remember the trig wheel, or you know how to do it using the hand trick, or you make the triangles, however you make it, that's the square root of 2 over 2 plus the square root of 2 over 2, which together is just the square root of 2. If you do the next one, which is the sine of 5 pi over 4 plus the cosine of 5 pi over 4, you've actually done this work already, because this is the same values as the one we just did above it, only they're negative because they're in the third quadrant. So we get negative root 2. And then the last one is the sine of 2 pi plus the cosine of 2 pi, which is also equal to 1. So again, it asks for what's the absolute minimum. The absolute minimum is right there. That is the very lowest y value we have, negative root 2.
I have a quick question.
Yeah.
Can you, is there a way we can go over the graphs of sine and cosine? I remember at the beginning of the year, we kind of went over the triangle stuff, but we never really went over the graph. And I haven't, the last time we went over that was pre-calc. So I don't really remember the graphs.
So the things that I know about the graphs that I have people remember is, if you draw the sine graph, it looks like this. This is 2 pi. This value is pi. This is pi over 2. And this is 3 pi over 2. This is 1. And this is negative 1. And the values that are really the most important ones are here, and here, and here, and here, here. So that's the sine graph. Okay. Sine y equals the sine of x. Looks like that. Okay. The cosine graph is really similar. It's actually just phase shifted over. The cosine graph, let me see if I can draw it in the same. I'll try to draw it so they're at least, they look sort of like they're in the same window here. Do my best anyway. The values that are in that we get from the graph, there's the two graphs right there, the sine and the cosine. They look the
Do we not need
same.
to know,
Say it again.
do we not need to know tangent?
Tangent, the easiest thing, I mean, tangent isn't bad, but a couple ways that I do tangent is I do y equals the tangent is the same thing as the sine over the cosine. And so tangent ends up having some, asymptotes. So tangent actually looks like that. That's what tangent looks like. I end up using sine over cosine instead of memorizing the tangent graph. That's what because I can get everything from the sine and the cosine graph. So I kind of hone in on the top two graphs, honestly, if I'm gonna do it. That can get me. So I don't want to memorize everything, because I mean, even though I actually have it memorized, I also try to figure out if I was a student, what would I need to have it memorized? And I think I can get everything from those two graphs. So that's all I tell you to memorize, because you can get everything from those two. Knowing that that tangent is the sine over cosine. Okay. That's, and 95% of AP questions ask you for sine and cosine. They don't really ask you to evaluate tangent anyway. They'll only ask you to evaluate sine and cosine. But that's a good question. Is that helpful enough, or do you need more?
No, yeah, that's helpful. I just never had the graphs written down, so
Yeah.
I'll just memorize that. Yeah.
Perfect. All right, let me see. I think we are going to 8 and then 9. So let's look at 8. So this is a tricky one, because I didn't really ever tell you what the second derivative test was. So if you're like, oh my God, I don't think we ever learned about the second derivative test, the answer is yeah, and I forgot that was going to be written that way in there. So that's my fault for not telling you that. But here's what you know. If you think about what the second derivative does, the second derivative gives you the concavity of f. Okay, so that's really what the second derivative test is really doing, is it's saying, okay, the second derivative is giving you the concavity of f. So when the second derivative is positive, f is concave up. When the second derivative is negative, f is concave down. And you get that from the chart. So if the second derivative is equal to 0, f is it doesn't have any concavity, right? Does that make sense? So if that's the case, and notice it's saying a local, the location of a relative minimum or a relative maximum. So remember that if f has a relative minimum, f looks like this. When f has a relative maximum, f looks like this. So notice when f has a relative minimum, what's true about the second derivative?
Is it like concave up or?
It is, it's the first, the function is concave up. So what's true about the second derivative then?
Oh, like it's positive or yeah, positive.
Exactly.
Okay.
And when f has a relative maximum, then the second derivative is negative. Now, if the second derivative can't be used to determine a relative minimum or relative maximum, that means the second derivative has to equal 0, because when the second derivative equals 0, we don't know what the heck's happening with f, because it's not concave up, it's not concave down. We're really stuck. So this particular question is saying, which of the second derivatives over here, when you put 2 in, do you get 0? That's really another way to saying this. Like if I were going to translate all this mumbo jumbo in here, another way of asking the question on question 8 is question 8 is saying which function from a through d does f double prime of 2 equals 0? That's really what that question is asking. Now, the reason I say it that way is, yeah, if that was the question, there isn't anybody in here that would have as much trouble with this problem. So a lot of times what you're doing on these questions is you're sort of going, okay, if I know all of the top information, and I can translate it into something easier to ask myself, then it makes those problems a little bit easier. And so this is saying, okay, the second derivative test, which it means just the second derivative, can't be used to conclude that at x equals 2, there's a location of a relative minimum or a relative maximum. So if the second derivative can't be used for that, the second derivative must equal 0 for which of the following functions. So what I circled there is really the question they're asking, is they're saying, which second derivative equals 0? Now, there's a lot of different ways. You could start this by saying, okay, well, I'm going to start with A, and then I'm going to go to B, and then I'm going to C, and then I'm going to go to D, and I'm going to find the second derivative, and I'm going to plug in 2, and I'm going to figure out which one equals 0. Now, you could go through all of those, but if I were doing it, I would start out with the easiest ones first and work my way to it and figure out if I can find one that where the second derivative, when I plug in 2, equals 0 the fastest. So here's what I would do. If this is my question, I'm going to say, okay, let's check C. C, if the first derivative is equal to 2x minus 4, then the second derivative is equal to 2. So it's not this one. Because remember, I'm trying to get this result. That's the result I'm after right there. If I can get that result, I'm good. Well, that's that one. That doesn't work for this one. So what's the next easiest one to check? Well, I'm going to D, right? I'm going to D right away because D is a little bit easier because D's second derivative is equal to 6x minus 12. So the second derivative at 2 is 6 times 2 minus 12, which equals 0. And I'm going, yippee, I got it. I don't have to check the other ones. Now, if I had to check the other ones would be, well, I'd check A maybe, but checking B would be a nightmare, and B would be hard. I mean, and let's be honest, if I got to D and that didn't equal 0, and I got to A and that didn't equal 0, and I did all the math right, the answer would be B, and I wouldn't have to do it, right? So on some of the level, we got to kind of go, what's the least path of least resistance on this? And that's how I would do that one, okay? But we never really talked formally about the second derivative. So if you were like, I didn't really understand, I don't have any notes on that. well, take a picture of that or something, because that's the second derivative test. It's a kind of a combination of the chart and all the information we get from the chart, which is why I didn't cover it, because I didn't want to cloud that for you, because you all pretty much understood the second derivative anyway. Okay, so let me get to 9, and I hope I can get through the other ones. Okay, so let's look at this one. So I got this graph, and notice it's the graph of the second derivative. That's a really, really important thing, because if you don't realize that that's a second derivative, you are going to be jammed up on this problem right from the get-go. So then it says the graph of the second derivative is given. F, on this interval, F has one critical point, and it occurs at x equals 6. Okay, well, so if F has a critical point when x equals 6, that means the second derivative, or sorry, the first derivative at 6 is equal to 0, which means it could be a relative minimum or a relative maximum. We just don't quite know yet. It'd be nice if we could test the sign of either one of those, but we can't really test the sign yet. Okay. But
Wait, why would f prime be 0? Wouldn't it be f?
no, because if f has a critical point at x equals 6, remember critical points are when the derivative is equal to 0 or undefined. So we got this. So now we go, okay, what else is happening? Well, notice that the second derivative of 6 is positive. Okay. So notice from the graph, f double prime of 6 is greater than 0, which means f is concave up. Okay, so we know f is concave up. And we really know that based on this second derivative, notice that from just before 1 all the way to 9, according to this, f is concave up all the time, right? Because the second derivative is always above the x-axis. Well, if we know that this is true, we already know that this is a relative minimum at the least. It's at least a relative minimum, right? We got a concave up graph. The first derivative is equal to 0. So we know it's not a relative maximum. We know it's at least a relative minimum. But the answer to this is this one happens to be an absolute minimum as well, because if this is the graph of the second derivative, notice that if this is the graph of the second derivative, if the second derivative just before 1, so somewhere around x equals 1, the second derivative is negative here and positive all after that, right? Does that make sense? That means f is concave down here and concave up all the way after that. Well, if a graph is concave up all the way after that, it doesn't really matter, but you know that this graph is going down like this, then turns concave up, stays concave up, and it's always concave up, but at x equals 6, we already established that that was a relative minimum. It's also the absolute minimum. That's a little harder question, but that's why B is the answer on that. And it has to do with the fact that we don't ever change concavity again. So once we start to go concave up, we can't get concave back down. We can't get this thing to go back down. And we already know it bottomed out. We already know that there was a valley there. And we know there was a valley there because of this work up here. Okay, I got 5 minutes. I got 2 questions to go over. If I go a little long, I'll continue to record. If you need to leave to do whatever you need to do, that's fine, but I'm going to keep on going. Okay. Okay, so number 11. I haven't done this one yet, so let me look at it. So you got a continuous function. So continuous is good information to know. I know that my function is continuous. It's continuous from 0 to 9, twice differentiable, which means I can find a first and second derivative, except at 6. So x equals 6. We got something goofy happening. Where the derivative doesn't exist. It doesn't say the function doesn't exist. It just says the derivative doesn't exist. We have all this stuff. Which of the following statements could be false? Now that's always, I'll be honest with you, that's always the hardest questions that we have, is when they say which one could be false, because that means you got to check them all. Okay. So let's look at this first one. Okay, let's look at this first. Let's look at A, and let's see if we can rule out A and see if we can figure out what A is. So for A, F as a relative maximum at x equals 2. In order for, now we know F is continuous, so we know it has, that F has no jumps, no holes, no asymptotes. So we know it's a clear, clean function in the sense that we can draw it without lifting our pencil. Now let's look at what happens at 2, okay? Notice that at 2, we don't know what's happening here. We know that the second derivative goes from negative to negative, so it's concave up to, or concave down to concave down. I think this is going to be really hard. You know, if you get a relative maximum, F prime needs to go from positive values to negative values. We know it goes from unknown to negative, so I don't know necessarily. I do know that F double prime needs to be F double prime, for it to be a relative maximum, F double prime would need to be negative. And we do have that. It's -1 right there. So I think this one could be true. So, but I'm gonna kind of keep that one in the back of my mind. But I think this one could be true. But I'm gonna move on to the next one and see if I can make sense of the next one. See if I can get the next one to be definitely. The graph of F has a point of inflection at x equal 4. So if F has a point of inflection, the second derivative changes signs. So when x equals 4, notice that the second derivative does change signs there. This is absolutely true. Does that make sense? Second derivative change signs there, okay? So let's look at C. F has a relative minimum at x equals 6. X equals 6. So let me see, let's see, a relative minimum. F has a relative minimum. F prime is going to go from negative to positive, and F double prime needs to be positive. Okay, if that's what we're going to have, that needs to be true. So let's see what's happening at 6 over here. At 6, we're going from negative to positive, and but this is going from positive to negative, which means it's going from concave down to concave up. Well, we could still have that happen. I mean, we could have a graph go from concave down to concave up there and still be a relative minimum. It could look like that. So that still might work out okay. Okay, so I'm more okay with that than I am with A. but let's look at 8. Let's look at D. The graph of f has a point of inflection at x equals 8. That's similar to what we did with C. So for a point of inflection, second derivative needs to change signs. And I don't know what happens at 8. So the second derivative, we don't know if the second derivative changes signs there. So I'm a little questioning about that one. So I'm going to cheat because we're running out of time. But when we go back to this, notice that D only relies on the second derivative. But notice this could work, okay? And remember, this says could be false. This could work, so that could be true also, right? I mean, we could have that work. And notice that we have this true, so this is okay as well. So the only one that really is a problem is D, because it only relies on the second derivative, and we don't know what happens there. We need it to have a sign change, but after 8, we really don't know. You know, when x equals 8, we don't know what's happening over here. So there's so little information over here. We just have that's the one that we're just the most unsure about, and that's why that would be the answer to that one. Okay, then let's look at this one. So this is the graph of f prime. The derivative of f, the derivative of continuous function f. So you know f is continuous. That's really important that f is continuous. So you know you don't have any holes or jumps or asymptotes in f. Which of the following statements is true about f on the interval -2 to 16? So if we need it to be true, f has 2 relative extrema. In order for f to have 2 relative extrema, and the graph of f has 3 points of inflection. So we got to think to the chart. Okay, I'm trying to get so I can see everything on here. So let's make this a little smaller. Do my best to. I just hope it's not too small for you. Okay, so for part A, if f has 2 relative extrema, f prime needs to cross the x-axis twice. And that happens, right? Crosses right there, and it crosses right there. Does that make sense? Let me just make sure. I think that I'm going to get the. And then in order to have points of inflection, so in order to have points of inflection, to have 3 point, what does it say? F has 3 points of inflection. F needs to go from, or f prime needs to go from increasing to decreasing 3 times. Well, notice it goes from increasing to decreasing 1, 2, 3, 4 times. So nope, that doesn't work. Does that make sense that that doesn't work there? Because it actually happens, it happens 4 times.
See, the question that I have about this one is like when it just jumps from the positive to the negative, does that count as like crossing the x-axis? Or does it touch the x-axis?
Actually, yes. So, so this is note 2, I think. Because it really happens 3 times, I would say, right? Because it goes from positive before whatever that is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 10, f prime is positive and then f prime is negative, which means you're going to have a point of inflection, or you're going to have a relative maximum there, right? So it actually has, based on this, f has 3 relative extrema and 4 points of inflection, right? So notice we have 3 relative extrema and 4 points of inflection based on what we look at on this, which is why the answer must be C. Hopefully it's C. Is it C? Yeah, there you go. Okay. So that's what we get on there. So hopefully that makes sense. But you're looking for changes. You're looking for, you need to cross the x-axis, or you need to go from increasing to decreasing, or decreasing to increasing. All right. Any other questions? Anything that I didn't do that you guys want me to do since you're still here? Okay. Then I'm going to stop sharing. And once I end the meeting, I'll put it on. I'll put it on